All right, so yeah, what I'm going to be going through this afternoon to start the data mining session is just an introduction to Scikit-Learn. So this is going to be, we've been having a lot of kind of theoretical and philosophical discussions. This is going to be very, very untheoretical and unphilosophical, but very practical. So essentially what I want to do in the next hour plus is give you an introduction to machine learning. You know, this is a term or a phrase that you hear thrown around all the time. And, most people have some idea that machine learning is important and some sort of powerful technique, but I have no idea what it is. So we're going to talk about what machine learning is, and then also practically how you can do machine learning, how you can try out these algorithms with this package called Scikit-Learn, which is Scikit. In the Python world, Scikit is something that's sort of an add-on to SciPy. That was decided 5 years ago, something like that. So there's a lot of different Scikits. There's Scikit Signal, there's Scikit Image, Scikit-Learn, Scikit whatever. So these are add-ons to the SciPy functionality, and Scikit-Learn is just the one that has to do with machine learning. So I have a link right here, and this is actually the Scikit-Learn website. And it's fun to poke around. There's a lot of different things that you can do here. They have an intro to some of the machine learning algorithms, the classes of machine learning algorithms, and then there's things on model selection, pre-processing. So if you're curious, you can go there and take a look. But I'll be walking through a few of these things in this notebook, Scikit-Learn intro. So just the outline, like I said, the main goal is to introduce central concepts of machine learning, what machine learning is, and practically how you can start doing machine learning using this package. And so we'll go through the definition of machine learning. We'll talk about data representations. This is pretty important. How do you take whatever data is out there in the world and go and turn it into bits and bytes that Scikit-Learn can use. I'll do an introduction to the Scikit-Learn API. It's a really nicely designed and regular API for machine learning. So once you have it down, once you've figured out how to use it, you can basically use any of the algorithms in the package. And all it requires is dropping in different class names. And then we'll go into the basics of machine learning, and machine learning is kind of divided into these two categories, supervised and unsupervised. And we'll talk about what those mean. We'll talk about the two main classes of supervised learning, which are classification and regression. And then a few of the main classes of unsupervised learning, which are dimensionality, reduction, and clustering. Now when we say data mining, this section is labeled data mining. One of the things that I think of as data mining is unsupervised machine learning. It's a way of figuring out what your data is telling you without having to put too many assumptions into it. So we'll see that. And then at the end, we'll talk a bit about model validation, so how to figure out if your model is doing well. And then at the end, I'll show you a little application which is interesting, actually, classifying handwritten digits. So given a sample of someone's writing, can you tell what digit they're writing? Whether it's a 1 or a 4 or a 9. And we'll see how to do that with Scikit-Learn. So not a lot of specific astronomy stuff today. This is just sort of kind of the introduction to the package, the introduction to machine learning in general. And from this, we're gonna jump off tomorrow and get a little more in-depth on some of these things. So tomorrow, I'll talk about, in the morning, supervised learning, and look at a couple supervised learning methods, how they work, what sort of insights you can gain from them. And in tomorrow morning's breakout session, we're going to use supervised learning to do some things like photometric redshift, to do some things like, what was the other problem I did? Oh yeah, photometric recognition of variable stars, and things like that. So that'll be the astronomy application tomorrow morning. And then in the afternoon tomorrow, we'll talk about unsupervised learning in depth and look at a couple unsupervised learning algorithms. And again, in the breakout, we'll apply those to some real astronomical data and see if we can get some interesting insights using these methods. So Any questions there about the outline of today and tomorrow? Does that sound okay? You all right with it? Good. Okay, so let's talk about Scikit-Learn. So I mentioned that it's this Python, this Scikit, this Python package add-on to SciPy. The goal of Scikit-Learn is to give access to well-known machine learning algorithms. So everything you find in Scikit-Learn is something that's been known in the computer science community for 10, 15 years, and it's well used and well understood. The bleeding edge, state-of-the-art, cutting-edge algorithms aren't really in there because that's not one of the goals of the package. A big piece of it, too, like I mentioned, is that there's a clean, well-thought-out API. And this has been kind of cool because the API of Scikit-Learn, the way to call these estimators and to do this analysis, has started to be adopted by other packages. So, for example, if any of you know Josh Bloom at Berkeley, he started this company called Wise.io, and what they do is they provide machine learning as a service. And they have Python wrappers for their machine learning implementations, and the Python wrappers use the Scikit-Learn API just as sort of a standard. So, and often when I write reusable code for astronomy, I'll use the Scikit-Learn API to make the estimators available. Scikit-Learn is built on NumPy, which is as you know, is the numerical computing, kind of the package that gives you data buffers and data arrays, and SciPy, which is a package that wraps all sorts of useful Fortran codes to do interesting scientific things. And the last thing I should mention is that Scikit-Learn is not really designed for big data. So people like to do machine learning on big data because those are buzzwords that get you jobs. And Scikit-Learn can't really do that. It's designed for small to medium data sets, though there is some work on extending it and doing some more interesting large data sets out of core, that kind of thing. But I usually think about Scikit-Learn as something that I use for teaching, for doing kind of day-to-day small problems, and for gaining insights about the algorithms, but you may have to go to more specialized packages if you're trying to, like run something on the entire LSST data set or something like that. But that's a different challenge.
What's your description of big data, like orders of magnitude?
Oh, so in this, when I say big data here, I'm thinking anything that doesn't fit in memory on your MacBook Pro. Right, so anytime you have to start worrying about where your data is living and having maybe different cores communicating with each other and data living on different machines, that's where Scikit-Learn sort of breaks down. Thanks. Okay, so let's ask a question. What is machine learning? And this is actually, machine learning to me just seems like it sounds more complicated than it is. But basically, machine learning is about building programs with tunable parameters. And these parameters are usually just arrays with floating point values. And these parameters are adjusted automatically so that the machine learning algorithm, by looking at some training data, can tell you some information about some new data. Now, if you think back to the last couple of days, you might think to yourself, like, what's the difference between this and just doing a maximum likelihood estimate, right? Like fitting a line to data, and then that line tells you about new data. The answer is there's no difference. Machine learning is just maximum likelihood estimation. And you define a model, you fit it to data, and then the model tells you about new data. So there's nothing new here that we haven't done yet. But the reason it's called machine learning is, actually I don't know why it's called machine learning, it's just model fitting. So what we're going to do, we have this introduction to machine learning. It's just an introduction to how to do model fitting in practice, how to use code to fit models to your data and learn things about new data. And we'll see some examples of that. So here's an example of, quick example of a classification algorithm. And this is one that we'll go through tomorrow. This is a little bit hard to see. Let me make it a bit bigger. So the classification algorithm, we have this two-dimensional data, and there's a group of points that are up on top, and there's a group of points at the bottom, and they have different labels, right? We have blue points on top, and we have red points or brownish points on the bottom. And a classification task might be to say, I want to draw a dividing line between these two groups of points. And so this is the dividing line that the algorithm came up with that divides those two groups of points. And now, so that's the model we fit to the data, right? And now what you can do is say, if I add another point to this plot, I'll be able to tell you based on that model whether it should be red or whether it should be blue, right? So this might be, for example, the G minus R color, and that might be the U minus G color. And then on the top, you have main sequence stars, and on the bottom, you have R O'Leary stars that you know from their periods. And then you go and observe a new star, you plop it down on that diagram, and you want to know whether it's main sequence or R O'Leary, and you figure out the result, right? That's exactly what we'll be doing with this later on. So that's machine learning. That's a classification algorithm. We're trying to classify these discrete labels of sources. And you might think to yourself, like, this is a little bit ridiculous, right? Like, that's all machine learning is? I could do that when I was a kindergartner. I could draw, right? So the thing about machine learning that makes it powerful, though, is that even though we're just looking in 2 dimensions here, we could do this in an arbitrary number of dimensions, right? So you can plot 2-dimensional data and do this. But imagine if you had 1,000-dimensional data, right? If you look at a spectrum is basically, a single spectrum is a point in 1,000 dimensions. First dimension is the magnitude in the first bin, then the second bin, then the third bin. And instead of plotting it as a line on a piece of paper, you could plot it as a point in 1,000-dimensional space. And these algorithms, these machine learning algorithms, will generalize up to lots of dimensions. So, if you plot 1,000-dimensional data, it might be hard for you to draw by eye a 999-dimensional hyperplane that splits those. But this algorithm can do that just as easily as it does it in 2 dimensions. So that's where the power comes in. So that's a classification task. Just in case you wanted to see that, I'm not just drawing something here, I'm actually doing an algorithm. You can load this code here. This is the function that I ran. And you can look through here, and I'm actually creating data and doing a classification and then plotting the results. So it's a real result that you can look at if you like. Another type of machine learning task is a regression algorithm. And this looks familiar, right? We have data and we're fitting a line to it. And the context here is that regression is rather than predicting discrete labels, red or blue, star or quasar, main sequence or R O'Leary, in regression we're predicting a continuous variable. So what we have here is we have a bunch of points that we know the x value and we know the y value, and we want to say, well, given an x value, can we predict what the y value might be? So we need a model that given x predicts y. And what we've done here is we've fit a line to the data. So this is exactly what we did on Monday, right? We fit a line to data. You know how to do this. You write the likelihood, or the cost function or whatever. You minimize the cost function and you get the result out. And so now the point is that if you add another observation here, another x value, you can predict from this model what the y value might be. So an example of this in astronomy is something like maybe photometric redshifts. So the x value here would be the photometric colors, U minus G or something like that. And the y value would be the redshift. So given some training samples for which you have spectra, you can define the model. And then given some new observations for which you don't have spectra, you can predict what the redshift would be. So regression, when you see regression, that's something that's predicting a continuous variable, where classification is predicting a discrete variable. And just like before, you might say, well, I did this in my kindergarten statistics class. I drew a line through data. And it's easy in 2 dimensions. But now imagine again if instead of having just one x, you measure 1,000 different x values. You measure 1,000 different features for these things that you're trying to predict. And you still want to predict what the y is. You want to predict some continuous variable. That's difficult to do just by eye, by plotting the data. But these algorithms generalize up to higher dimensions, and you can do these more sophisticated problems. So that's machine learning in a nutshell. You're fitting models to data, and the models generalize the new. So the first thing you need to do is figure out how to get your data into a form that Scikit-Learn can use. So this is the data representation question. And data in Scikit-Learn, I'm going to make use of this. I know I told you I wouldn't make use of this, but I just like drawing. So data in Scikit-Learn is, it comes in a matrix. So think of a two-dimensional matrix right here. And each row of the matrix is one sample. And each column of the matrix is one feature. Now, what do I mean by samples and features? So, a sample is something that it's an object that you're interested in. So, an object would be like a galaxy or a star or we'll see later, a flower or anything you're observing. The sample is the actual object that you're interested in. And the feature is the measurement you have about it. So a feature might be the U minus G color, or the feature might be the degree of twistiness in the spiral arms that you somehow measure. Or the feature might be the length of the flower petal that you're looking at, right? So the data is in this matrix that's usually called big X. And the size of the matrix is the number of samples, n underscore samples, by n underscore features. So this is our X array that gives all the features of the data. And then if we have labeled data for supervised learning, the next thing that we have is basically a vector. This is y, just a one-dimensional vector, and the y vector contains the labels. So in this case, the labels for classification, what we saw before, this might be red, blue, red, red, blue, red, blue. But you don't actually put the string red or blue in there. You'll just use some number like 1, 0, 1, 0, 0, 1. So these are numerical code that represents the labels that you're looking at. So just to make this more concrete, right? If you're looking at galaxies and you're trying to classify, like, say you want to classify the Hubble. Let's do a regression problem. Say you want to classify the photometric redshift of galaxies. You have a bunch of galaxies here where each row tells you one galaxy. Each column tells you some photometry color, G minus R, U minus G, R minus I, whatever, for each of these galaxies. And then the labels here would be the redshift of each galaxy. So the first redshift corresponding to the first row, second redshift corresponding to the second row, etc. So that's how you make your data. And one thing you'll notice in that is that because you have this in a matrix here, you need to make sure that for each of your samples, you have the same type of observations, right? Machine learning, in the way Scikit-Learn is created, machine learning won't work if for one galaxy you just measure the U-band, and the next galaxy you measure how twisty the spiral arm is, and the third galaxy you measure, the absolute brightness or something like that. You need uniform measurements for each one. You need to have the same data about each of the different objects. And that can be relaxed and kind of in more advanced applications, but for basic machine learning, that's what you need. You need the same measurement for each of your objects. So this is what I've said right here. You have n samples, which is the number of samples, number of objects you have, number of individual things you care about. And n features is the number of features or the number of distinct measurements you have for each sample. And your matrix is number of samples by number of features. And I should have written here that y is, the length of y is number of samples. Because you have one label here for each of your rows of your matrix. Yeah,
how independent should the features be among themselves?
The question is, how independent should the features be? It doesn't really matter. You can do anything. But for each individual algorithm, it might perform better or worse. But that for the overarching, just how to get things in there, it can be anything you want. Yeah.
Why do you distinguish the features from the labels? It seems to me like you could put the labels as another feature. Why do you do that?
Yeah, the reason you distinguish between the features and the labels is because generally the labels are something you only have for your training set. So for photometric redshifts, you have a certain collection of galaxies for which there are labels. And then the labels are things that, given another set of features for unknown objects, you can predict. So we get these features for a new set of galaxies, and then we can predict what the label is, we can predict what the redshift is.
So ultimately, that's the thing that you want to get out. And this
Yeah.
Is you're telling it, listen, I know this one, so you should get this.
Yeah, so the labels are you can think of them also as unknowns. At first, for your training sample, they're known, but then for the rest, they're unknown.
So the label is the thing that allows you to the classification. That's what label means.
The label is the thing you're interested in predicting. Yeah. Thanks. Other question? Yeah.
Do you need a value for every feature? I mean, you can have a sample with certain math.
Yeah, that's a good question. The question is whether you can be missing features and
some samples, so it goes to.
So for the most basic algorithms, for the kind of level 1 machine learning, you need all this data to be in here. You can't have any missing features. If you go to more advanced algorithms and more advanced approaches to the algorithms, you can relax that a little bit. But in general, and the things we're going to be looking at today and tomorrow, we're going to have no missing data. So missing data is actually a pretty complex question. Any other questions? Oh, one more.
Yeah, so how does the performance of the method depend on the size of the data set?
So the question is, how does the performance depend on the size? And that completely depends on the method. So there's some that scale really quickly with our large data sets, some that are really slow. And we'll get into that a little more tomorrow, I think, when we talk about those in detail. All right, so let's look at a simple example. And this, if you've ever studied machine learning, or if you've ever done anything along these, for some reason, the first example that everyone uses is this iris data set. And just to conform to everyone else, I'm going to use the iris data set as an example. So in this case, you can think about the iris data set. This is a botanist went out into the woods and wanted to take a look at some irises and ask if he could figure out what species the iris is. So they had 3 different species of irises in this particular woods. One was the iris setosa, which looks like that. One was iris versicolor, which looks like that. And one was iris virginica, which looks like that, right? So now you have these 3 different types of irises. You want to classify what kind of species they are. So in this case, what does a number of samples refer to? In this case, we're not going to do anything that sophisticated. What we're going to do is look at the iris data set and that's loaded into Scikit-Learn. And the features we're using are the length of the sepal, width of the sepal, length of the petal, width of the petal. And then we have our 3 target labels, which are these 3 iris classes. They're 3 species names. Yeah, this is the biology thing. And the big guys are the petals, and the little guys are the sepals. Yeah. Yes?
Sorry, Jack. Are we learning from these images, or do we have somebody go out and measure the plants?
Yeah, fortunately, someone has gone out and measured the plants. So these are just examples of what they look like. In the data set we have is some botanist who actually went out into the woods with his ruler and started measuring things and writing it down. So because this is kind of a standard data set, this is one of the data sets that Scikit-Learn has available. And you can just say, I want to load the iris data. And this is, we'll see in a second, but Scikit-Learn has a lot of data sets that you can play around with, and it's really helpful for for demoing things and just for exploring different algorithms. The keys in here, this tells us which, oops, I want to make that smaller, so can you guys read that or should I make it bigger again? That's fine, okay. So the keys in here are the things that are part of this data set. We have the target names, which are the names of the species, the data, the feature names, the target. So let's take a look at this. If we look at the iris.data, we can ask what the shape is. And remember I told you the shape is number of samples by number of features. So we print that out and we see that we have 150 samples by 4 features. Right, so that's 150 different flowers, and for each flower we have 4 measurements. And just to take a look at the first row of this data, the petal length is 5.1 centimeters, the width is 3.5, the sepal length is 1.4, and the width is 0.2. So that's our data. This is for the purposes of the algorithm, this is everything we know about that iris. Right? And if we compare this, we have the iris data shape and the target shape. Data shape is 150 by 4, so that's that X matrix that I wrote right there. And the target shape is 150, so that's that Y vector that I wrote. And to take a look at these targets, it's just a bunch of 0s, 1s, and 2s, right? This 0 is one species, 1 is another species, 2 is another species. And this is, the target names gives you the kind of dictionary of how to interpret that. So all the 0s are Iris setosa, all the 1s are versicolor, and all the 2s are virginica. So this is our data. We've distilled the real world of messy flowers down into one nice little data set that's numerical and regular and square and matches and everything like that. So this is, actually I should say right now, this process right here is called feature engineering. You know, you take the messy real world and you turn it into something clean that your algorithm can use. And feature engineering is the most difficult part of doing machine learning and doing statistics in general, right? You have to figure out what numbers to put into your algorithm, and that's where all of your expertise in your own area of astronomy is really vital, because you want to know exactly how to pull data out of the real world. Yeah. So the question is, can you look for features automatically? I mean, you can. There are ways to, given a list of possible features, there are ways to figure out which ones are most useful, so to learn the feature importances. But you really need to use some human insight to figure out what those possible features are, right? Like, I don't know of any machine learning algorithm who could take the raw output of Gaia and tell you, oh, this is something interesting about the universe, right? You need a human to look at that data and figure out what to plug into the algorithm. I don't know. Maybe that's the next thing. Like, we need IBM Watson to tell us what the features are or something. But yeah, so machine learning is not a magic bullet. It's just a way of, it's a class of methods that help you look at your data. Any other questions on that? Yeah. So you could do things, and given some features, I want to say more on that. Given some features, like for example, if you just plugged in the pixel values of this image, you could do a machine learning algorithm on it that would say, oh, here are some interesting features in the image. Here's some interesting aspects of the image that might correlate with the real world. But still, you're telling it the features are these pixels. And that's what you're working on. So features have to be some sort of regular data. Yeah.
So it's important that the number of labels is equally distributed, or more or less equally distributed among the different classes?
Okay, so the question is whether the labels have to be equally distributed, like balanced numbers in each class. And that's one of those things that depends on the algorithm. Some are better with balanced, and some can handle imbalanced features. And that's one of the things you have to understand about your model when you apply it.
When you consider individual pixel values as a feature, does it do any sort of realignment which might suggest that one pixel is really better
Yeah, so
than another one.
the question is when you use pixel values as a feature, is there any sort of realignment that happens to kind of say that this part of the image is the flower and the other part is the background? Maybe that's another thing that's difficult. You know, if I had an iris that was a thumbnail with 100 pixels versus a high-resolution image with 1,000,000 pixels, like you can't really put that in the matrix, right? You can't have a row of 1,000,000 followed by a row of 100. So
one case was the iris was on the left and the other the iris was on the
yeah.
right.
And that's the other question. So if the iris is on the left versus the right and the pixels don't line up, in that case you want to do some feature engineering. So you have in your head, you know that kind of this is the iris, this is the interesting part of the image, that's the interesting part of the image. You can do that by hand, by cropping the image and redoing it. There are also image processing techniques that are really nice for feature extraction. So you could do something like define a filter on your image that would actually find the interesting piece, and that's what's done in practice. So, like you load your picture of your friends exploring Madrid onto Facebook, and Facebook has this feature extraction thing that finds the human faces and boxes them, and then runs those human faces through some sort of trained classifier, and then says, do you want to tag Andy or whatever on the picture, right? So that's all those layers that are going on, right? Is that clear, all that? Yeah. Features and inputs and everything. Okay, so we have all of this, and now let's one of the things that's useful when you get a data set like this is just to visualize it. So kind of see what's going on here. So this is I'm plotting the x-index versus the y-index. So this is sepal width versus sepal length. That's kind of nice. Let's see something else. Sepal width versus petal width, or sepal length versus petal length. You start to see, oh, this is interesting. This class is kind of all off by itself in this projection. And these are pretty well separated. There's something going on. You can imagine maybe drawing a line right here to separate those two, and a line right here to separate the rest. Let's take a look at the petal, the width versus the width. You see the same sort of thing here. So this is the data exploration. Once you get data, it's useful just to plot a few views of it and see what it looks like, just to understand what's there. And if you did this and you saw that one of the sepal widths was 5 kilometers, you would say, oh, my data needs to be cleaned up. That's obviously a bad value, or a really, really interesting flower. And this right here is kind of a rudimentary form of dimensionality reduction, right? We're taking 4-dimensional data and we're projecting it down to 2 dimensions to explore what the data looks like. And we'll see a little bit later a way to do dimensionality reduction automatically. So instead of just saying x versus y, 2 versus 3, we'll have an algorithm that will learn from the data what might be the most interesting projection to look at. That's an example of an unsupervised algorithm. So, I just did this quick exercise. Good job. So basic principles of machine learning. We're going to look at what to think about with machine learning, and then how to do these things using the Scikit-Learn API. So the Scikit-Learn API is built around this estimator object. And if you've used Python, you know that Python is object-oriented, which means basically you encapsulate data and functionality all into these little code objects that you can use. And Scikit-Learn is based upon that. So every algorithm, every machine learning algorithm has some class that it's associated with. So if you want to do a linear regression, you get the linear regression class. If you want to do a support vector machine, you find the support vector machine class. And then once you have that class, you can start. Once you have the class and you have the data, you can start doing things. So this is a linear regression. This is the Scikit-Learn method of what I talked about for several hours on Monday, which is fitting a line to data. It's a little more general than that, but basically linear regression. The first thing you do is that you instantiate this class, and one of the key pieces of Scikit-Learn is separating the models from the data. So the models are these things that live all by themselves, and you can kind of point them at data, but the models themselves are objects, even if the data isn't plugged into them. So you instantiate the model without giving it any data. And when you instantiate the model, you tell it what sort of model you want. And these are known as model parameters or hyperparameters. So right here we're instantiating the model, and we say, this is a linear model where the data is going to be normalized before I fit the line to it. Right? So you instantiate that model, now you have this model object, and this model object has all sorts of attributes. And in this case, the model.normalize is true. That's because we told it to be true, right? So we can print the model, and we can see all the different attributes that are in the model. And some of them matter for the results, and some of them don't. Copy X means that whatever the input is, it's going to copy it before it modifies it, so it doesn't modify the input data. Fit intercept, that just tells us that if we're fitting a line to data, that we're going to allow the y-intercept to float. And normalize tells us we're normalizing the data first. So again, I want to emphasize the models are separate from the data. So this is a model that's out there, and you could take this model and fit it on any variety of data that you plug in. So now let's think about what we want to do with some data. And just to make it easier, we're going to do y equals, what did I say here, 2x plus 1. So this is some points along the line. We have our x versus our y. And we want to fit this model to the data. Now this is let me just print these. If we print x and we print y, you'll see that they're both one-dimensional arrays. So we actually need to remember this. The x array has to be two-dimensional, and the y array is one-dimensional. So in this case, instead of just an x array that's one-dimensional, we'll add a new axis to it like this. That's the way to do it. And we'll turn it into this 10 by 1 array. And that'll let us stick it into the estimator. This might seem a little bit excessive, but in most cases you'll have many, many more than one feature in your models. So it's just these simple special cases that this usually applies. So now we have our two-dimensional X array, number of samples by number of features. We have our Y array of labels, which is just the number of samples. And we do model.fit. So this is when we take our model object and we say, given all those parameters, let's fit our model to data. And that will adjust some sort of parameters in the inside of the model. It'll tune the model and make that model fit the data. And if you want to know what parameters were fit by your model, you can just do, in the IPython notebook, do model dot and then tab completion. And anything, the standard in Scikit-Learn is anything with an underscore at the end is something that was fit to the data. So this coefficient is something that was fit to the data. Intercept is something that was fit to the data. Rank was something, residues, singular, all these things were derived from the data itself. So let's take a look at some of those. Let's look at the coefficient and the intercept of the model. And we see that the coefficient here is a 2, and the intercept is a 1, which tells us, if we look up here, hey, 2 times x plus 1, that's our model. So if we're doing supervised learning, what we saw in our scene here is supervised learning is when we're trying to predict some value for data. We train the model, and we have some new data, and we want to predict the Y value. So some examples. Given a multicolor image of an object, determine whether it's a star, quasar, or galaxy. Or given a photograph of a person, identify the person in the photo. You might have several billion photos in the Facebook archive, and based on that, you want to try to identify who is who. That's an example of a supervised learning problem. And then things like, given a list of movies a person has watched, or a list of things a person has bought on Amazon, figure out which ads to send them, or which movies to suggest. So this is why machine learning is so popular in the world right now, is because everything that happens online is this machine learning algorithm. You type the first 4 letters of your name into Google, and if it auto-completes it, that means Google has learned a model of the world that includes you, which is kind of fun. Anyway. So that was a regression example. Let's take a look at a classification example. We're going to use the iris data here again. So we load the iris data. We get for short, we're going to call the data in the target X and Y, like I did up there. That's kind of the standard that I tend to use. Now we're going to create the model. This time we're going to use a k-neighbors classifier. So this is a classifier that says, go into my parameter space, compute the distance from this unknown point to all the other points, and give me the label of the one that's closest by. That seems reasonable, right? You figure out which has the nearest sepal length, nearest petal length, etc. So we're going to fit the model to this data right here. We're going to fit it to X and Y. And then this is something I didn't show you before, but what you can do with most models, that you can call predict. So you imagine you go out into the woods and you say, I have found an iris that has a petal length of 3 centimeters, a petal width of 5 centimeters, something like that. And I want to know what it is. I'm going to call on our model, I'm going to call predict and get the result. And then let's see which iris that result is. The result here is Virginica. So we've just done machine learning, right? We've fit a model to our data, our known data. We've asked what the answer is for this unknown point, and it gives us the species. And we're done. Now we don't need botanists anymore. Well, not really. We need someone to do the feature engineering for us. Yeah, so that's basically a classification. And I've made this little function here. What this did is went through the entire parameter space here and asked, given this particular point, what is the classification using this k-nearest neighbors? And this is one way to visualize the output of the model, right? We have all these inputs that look certain ways, and then given a point on this space, this will tell us where, actually, I'm trying to remember what I did in here. So this will tell us basically what the nearest neighbor is, I think. I'm confused by that point right there, because there should be a little green splotch around it. There's something in the model that I did differently here. It might have been something like using the 5 nearest neighbors and averaging the result, so you can do that as well, and we get versicolor. Was that different? If I use the 1 nearest neighbor, yeah, so if I use 1 nearest neighbor, I get Virginica, but if I use 5 nearest neighbors, I get versicolor. So this tells you that these things matter, right? These hyperparameters that you put in can change the results. So you need to make sure that you're choosing a suitable model, and that's one of the things we'll talk about tomorrow. Yeah?
You instead of just putting this new data, which is going into the model, and instead of giving it a classification, you give could you give a probability?
Yeah, you could. And some estimators have the probability prediction. I think this is one that has it. Let's see. Let's do iris.predict. Oh no, I'm doing knn.predict, right? Yeah, so there's this predict proba method. So that's predict probability, and let's look at this one. So given this model, it says the probability is 0% that it's the first species, 80% that it's the second, and 20% that it's the third. So this will work, some estimators have this, just depending on what's going on internally. Some can handle probabilistic prediction and some can't. So, other questions about that? Yeah?
Sorry. It seems like it's distributing probability among the three of them, like as one distribute. Could it be possible to get a high percent probability for one of them and all for the others? But you know what I mean?
Oh, so the question is, could you get?
It looks like now it's forcing to have a number on each of these.
So you're asking if you could get 100% 0 and 0?
Or even 80% 0.
So in this case, this is actually a probability. So you're asking if the model can tell you if there are features that, or if there are labels that we don't know exist.
Because then it's telling you like it has to have another kind of.
So that's a good question. So so in this case, no. In the regular classification, it'll only tell you probabilities or labels from among the labels that you've asked for. But what you're asking for there is what you're saying is I have this data and I want to know if it's weird, right? Compared, and that's something that's called an anomaly detection problem, and that's an example of an unsupervised problem. So there are methods in Scikit-Learn where you can ask whether your data is anomalous given a training set. Anyway, so we can do the same thing with regression. Actually, let me look at what we're doing here. We're creating an X array. We're creating a Y array. We're going to use this random forest regressor. So this is starting to look familiar. You instantiate the model. You fit the model to the data. You have some unknown, and then you call predict on that unknown data. And then we can plot the data plus the model that it's fit to it. So this is a random forest. We'll see more about this tomorrow, but a random forest is a non-parametric estimator that can really flexibly fit the data here, right? So this is kind of like, this is probably overfitting the data. It's fitting the noise more than the model itself. And we'll see how to diagnose whether that's happening tomorrow. But again, the point here is that you create the model. The model stands alone without the data. You fit the data to it. You call predict on some new data, and you get some new labels for that data. This is practically how machine learning works. So up till now, I've been talking almost entirely about supervised learning, which is where you have labels. You have things that you want to predict. Unsupervised learning is where you forget about this Y array, and you start asking, just given my data set itself, what can I tell about the data? So some examples of this are things like dimensionality reduction, I mentioned. If you have 60-dimensional data that you want to view in lower dimensions, you can do that. Clustering, which says maybe if you look at that iris data and you don't have any labels and you just want to know whether there's some distinct species among that data. And then things like density estimation, and this can help with the anomaly detection that we were seeing earlier. So just as an example of dimensionality reduction, there's this algorithm called principal component analysis, which you might have heard of. And I'm going to go into this in more detail tomorrow because it's a really important way of doing data mining and data exploration. But essentially the way you do it, without understanding yet what's going on, the way you do this in Scikit-Learn is just like what we've seen before. You instantiate the model. We're going to say we want 2 components. That's our model parameter, our hyperparameter. We fit the model to data. And notice the distinction here. Instead of passing a Y to the data, we're just passing the data itself, right? Unsupervised learning doesn't know anything about the labels. It just knows about the data. And then in this case, instead of predicting, we're going to transform our data into some reduced dimensionality data set. And then all this right here is just plotting the result. So here's our reduced dimensionality, right? We've taken our 150 by 4 matrix, and we've reduced it to a 150 by 2 matrix using some sort of model. In this case, we're maximizing the covariance in these two coordinates, essentially. And this is our projected data. So remember, our model knew nothing about the Y values. So as far as the PCA was concerned, what we were looking at was something like this. And then once we have that projection, just for the sake of visualization, we're going to add back in these y values just to see how it's related to the species. And the cool thing here is that given just the data itself, our PCA learned a projection that's actually, it actually has some information, some pretty good information about the species, right? So this tells us that something fundamental in the data is related to those species labels, which tells you that the botanists that decided on these species labels actually probably knew something, right? Actually knew what was going on. Anyway, so that's a dimensionality reduction one. Clustering is one where if we look at this data, we might ask, you know, if not knowing any of these species labels, could we find clusters in the data? And again, this will look familiar. We instantiate, we import the k-means class. We're going to use a k-means cluster here. We instantiate the models. We're going to tell it that we want 3 clusters. We're going to fit it to the data. And in this case, again, we don't have a y here, right? We're not telling it any information about the labels. We're just giving it the data. And then given that data, we're going to predict what the labels might be, given no training data at all, essentially. We're given no labels, we want to predict what they are. And this is what we get out. So, you know, just comparison, these are the real cluster labels right here. And the unsupervised cluster labels right there. So it actually pulls out this as being a cluster by itself. So it identified this species without knowing anything about it. And then this other one kind of divided it in half because there's not much information there. So that's an example of unsupervised learning. All right, so just as a quick recap, in the estimator interface, what you have in all estimators, you have this fit parameter that takes either fit xy for supervised, or it just takes fit x for unsupervised. In supervised estimators, you have this predict method, you have predict probability method, things like the score function, this asks how well the model is fit. And then in unsupervised estimators, you also have things like transform, to transform the data to a new representation, or things like fit transform, which actually fits and transforms the same input data at the same time. But the point to take home is that models are these things that you instantiate, they're class instances. You give them data by calling the fit method, and then you do something with the result to kind of figure out what's going on with the model, whether it's a prediction or a transformation. Yeah?
How are different units treated by the unsupervised methods?
Different units. So the question is, how are different data units? I mean, if you have one feature that ranges from 0 to 1 million and another one that ranges from 0 to 1.
I mean physical units.
A physical unit.
Yes, for instance, if you apply a PCA algorithm, which eventually would result in the linear combination of the original quantity. Is this quantity all needed to have the same physical units, or the algorithm is clever enough to find the proper reorganizations?
So the Scikit-Learn knows nothing about units. The numbers you put in are just raw numbers. So sometimes some algorithms are basically scale invariant, so it won't matter what units you're in. Other algorithms actually depends on the scale will change the results. So this is one of those things. There are ways to pre-process the data automatically to take out those effects. But again, you need to understand which algorithm you're using and what characteristics it has, because it'll treat it differently. Yeah?
In the K-means example, you plot the extra juice with extra juice, but extra juice was produced using PCA. Am I missing something?
Yeah, that's a good point. So here I plotted the X reduced, and that's mainly because I don't have a 4-dimensional plotting package. Right? So we're training on the X data, so we know K-means knows about the whole thing, but just to visualize the result, we're using reduced.
So what extra juice is produced by PCA transform? What does that do?
What PCA transform is doing is it's taking the data and reducing the dimensionality by doing a rotation in the parameter space. So we could have just as easily plotted the raw data, right? Something like this, and seen what k-means did. And to get an idea of what it looks like, we'd have to plot every pair of dimensions and all that. But instead, we already have this reduced dimensionality representation, so this just helps us kind of visualize the data set without having to plot all 4 dimensions.
Okay, so the axis parameter, the axis units are not any kind of length or...
Yeah, the axis units here are 0.362 times sepal length minus 0.082 times sepal width plus 0.857 times petal length, etc. Right? You can interpret the output that way because it's just a linear combination of the inputs that gives you that.
The k-means is in the labels here.
Yeah, the k-means here gave us a new set of labels for the data. Yep.
How do you get in the PCA algorithm the fractional variability of each component?
I'm going to answer that tomorrow because we're going to go into the details of PCA. So rather than diving into that now, and most people probably don't know what PCA is, then we can do that tomorrow. Because the one thing I want to do before, I'm going to skip this for now. In the last 5 minutes, I want to show you just a quick application on some data that's a little more interesting than the irises. This is something that, given a data set, how you might approach it. And the data set that we're going to look at is these handwritten digits. So again, we can import this from data sets, we load the digits, we look at the images, and the shape here is 1797 by 8 by 8. So what we have here are a bunch of little 8 by 8 thumbnails, actually 1797 to be exact, 8 by 8 thumbnails, each of which is a little clip of a handwritten digit. So this is the data we're looking at. We have 0, 1, 2, and in the bottom left corner I put the labels. So each of these is 64 pixels representing some digit that someone wrote, and we have the labels there. So the question we want to ask is whether we can train a classifier that, given a new unlabeled digit, would be able to tell you what that digit is. Right? So this is our supervised learning task. And the feature selection has already been done, meaning that we've already zoomed in on the digit that we're interested in and made it a common resolution. So we have nice clean data to start with. So the images that we showed there are almost 1,800 of them, and they're each an 8 by 8 patch. And this is what the data looks like. If we ask for the data instead of the images, what we get is a flattened version of this. So this is just a 1797 by 64 array. So we take this 8 by 8 array in each row and flatten it out into a single row. So this means we have 1797 samples and 64 features, right? 64 pixel values. So you can think of these image data as living in a 64-dimensional space. Each handwritten digit is a point in some 64-dimensional parameter space. So, and then each one has a label that just tells you what the actual value is, whether it's a 0, a 1, a 2, or all the way at the end, a 9 or an 8. So yes, 1,800 samples, 1,797 samples in 64 dimensions. So, as usual, the first thing you should say is, I want to know what my data looks like, right? But I don't have, a 64-dimensional plotting package, let alone a 4-dimensional plotting package. So let's see what it looks like in 2 dimensions if we reduce the dimensionality. Previously, we used principal component analysis to reduce dimensionality. We'll talk about that more in detail. Right here, I'm not going to say much about it, but I'm going to use this isomap, which is an isometric mapping dimensionality reduction. This is a manifold learning algorithm. And again, this will look familiar. We're going to import the class. We're going to instantiate the class to create a model and say that we want 2 components to come out of this model. And then we're going to call this fit transform method, which takes our data, fits it, and then transforms it, and then gives us a projected output. And just to do data projected.shape, we see that now we have 1,797 points in 2 dimensions. So that's a little more reasonable to handle for plotting, right? So let's plot those and take a look at what they look like. So here is our projected data. You can see the color bar goes from 0 up to 9, and it's a little bit difficult to see, but that's all right. So this is our projected data, and this is a nice step because it actually gives you some insight into what your data looks like. So for example, we see that the black points, the zeros, are sitting out here all by themselves a little bit, right? And the way I interpret this is that out of all the digits, if you think about them, the zeros are the ones that are empty in the middle. Most other digits have some ink in the middle of the plot, but the zeros are empty in the middle. So it means that, that they sort of are distinct in that way. It's probably that feature those middle pixels that are driving this separation. But there are some others that, if you write the digit in a weird way, it's sort of empty in the middle. And one of those might be the 6. So these yellow points are 6. And it makes sense, right? If you have a whole bunch of handwritten 6s, and some of them are a little sloppier than others, the 6s might start looking a little bit like zeros. And you end up with that right there. And doing this sort of thing, you can reason about the features you have in your data and what the relationship between the different labels are. And we can only do this because we did this unsupervised learning and projected it down. It would be very difficult to do this by plotting all the 64 dimensions against each other. Right? This gives us some insight into the data. But this is nice because this tells me that a suitable machine learning algorithm should be able to separate the zeros from the 5s, or the zeros from the 1s pretty easily. So this gives us insight into, machine learning might actually work here for this data set. So let's give it a shot. Yeah?
Space in the middle of that.
Space in the middle? No, this is one of the things with manifold learning. I mentioned this is isomap, which is a manifold learning thing. The output dimensions here are notoriously difficult to interpret. So it's hard to draw any conclusions aside from the relationship between the blobs. I know people who have tried, or I know papers that have tried, and I'm not quite convinced by them. So let's do some classification. One thing about classification is if you give data to a model and then ask the model about the data it's already seen, that's cheating a little bit, right? Because it's already seen that particular data. The real test of a model is how it performs on data it hasn't seen yet. So what we're going to do is we're going to split our data into a training set and a test set. And there's this nice train test split utility that lets us do that. And what we end up is a training set of 1,350 and a test set of 450 results. And that'll let us just evaluate how well the model's doing on new data that it hasn't actually seen yet. And in this case, we're going to use the logistic regression. This sentence is not complete. We're going to use the logistic regression, and as we've seen before, we're going to instantiate the model. Here we're going to use an L2 penalty in our logistic regression. We're going to fit the training data and then get some predicted labels by calling the predict method on the new data. So we'll do that, pops out pretty quickly. And just to see how accurate we are, there's this nice accuracy score metric that takes the true values and the predicted values. And we can see that we're just less than 95% accurate. So that means that 19 out of the 20 of these values have been correctly predicted by our model. That's kind of nice. One thing that I like to do is kind of see where the model is getting confused. So we can use this confusion matrix that basically gives a plot of the predicted value versus the true value. And a perfect classifier would just be a diagonal stripe down the middle here, and anything that's slightly off would be on the outside. Can you guys see that there's any off the? We can't really see that. Let's make that let's make this a log of the image and see if that works better. Yeah, now we can kind of see where this off diagonals are. So this is interesting to me, right? We're saying that if sometimes when the true value is a 1, our model is calling it an 8. So that means that, I guess I could see when an 8 is sort of squished, it looks a little bit like a 1. Or suppose sometimes when the true value is a 9, our model is calling it an 8. This sort of gives us an idea of where our model is messing up. And we can see this a little better if we actually plot the predictions if we plot some of the data with the predictions and the mishaps. So here we see all the red ones are ones that were mislabeled. So this is probably a 4 that our model called an 8. This one right here is something, but our model called it an 8, and that was wrong. And this one was something. So you can see the ones that are, you can kind of see which ones are messing up, and you can get an idea of what the model might be doing wrong here. This is my favorite over here. That one, we called it a 1, which, you know, I would probably call that a 1. You don't need a logistic regression to mess up on that one. So this gives you, oh, this is amazing. Like, this is a 1, and we got that correct. Look at that. So you can kind of see what's going on with the model here. But this just shows you how, in a couple commands, with a little bit of understanding of the utilities in Scikit-Learn, you can do something that's kind of cool, right? We're recognizing handwriting with 95% accuracy. And we haven't even done any model validation and more sophisticated things. I've done this before with a more sophisticated model and actually doing cross-validation, and you can get this up to something like 99.6% accuracy on these things. So we're out of time for right now. We have a coffee break, am I right? Yeah. Yeah, so we have a coffee break, and afterwards I have a little exercise in the notebook that will allow you to start actually applying some of these models on some real astronomical data to get practice, practice importing and instantiating and fitting and predicting with models. So that's it for right now. That's the basics of Scikit-Learn.